So I'd like to present work that we've been doing at EPFL over the last 2 years, and unfortunately the presenter of this work, Ewald Verhagen, who was the first author on this report here, was not able to come and attend CLEO, so I'm stepping in. And so my name is Tobias Kippenberg, and we work at EPFL in Switzerland, which is the Swiss Federal Institute of Technology. Now, let me start out by opening the session on optomechanics by just noting that mechanical oscillators are really ubiquitous tools in both science and technology. And to give you just a few examples, which of course many of you are very familiar with, if you take, for instance, atomic force microscope here, mechanical cantilevers are used in essence to probe nanoscale phenomena. And the idea of the cantilever here really is to work as a transducer. You take, in essence, a small force, say a force that's in a very extreme case caused by, say, a single spin interacting with a magnetic tip on a cantilever, and you transduce this force into displacement, and then in a subsequent step you read out the displacement optically to make, for instance, force measurements. So this is an example where mechanical oscillators are routinely used to make, in essence, reconstructions of atomic surfaces, or as in this beautiful work by Dan Rugard at IBM a couple of years ago, in fact, the sensitivity was pushed to its very limit, where it was possible to observe actually the presence of a single spin inside a matrix measured by the so-called MRFM method. Mechanical oscillators are also used for timekeeping. Many of you have cell phones, and in each of these cell phones there typically are these F-bar resonators. So these are devices actually that are used to perform filtering functions of RF signals. And you can do this in a much more convenient way using mechanical oscillators, in particular since, say, discrete LC circuits would never give you the same kind of quality factor in resonators. Now, in all of these applications, of course, what is the case is that the mechanical oscillator, in essence, is probed or used or functioned in a completely classical realm. What this means is that if you look at a mechanical oscillator and ask how many thermal quanta do you have in the oscillator, then kVt, the thermal energy, is much larger than the energy spacing of the oscillator. Okay, so you're typically on a very classical regime. Now, at the same time, if you ask at what scale do quantum phenomena happen, well, first of all, if you have a 1 gigahertz oscillator, you would require to have a temperature of about 50 millikelvin to take out all the thermal quanta. At the same time, if you're interested in to probe the displacement, of such an oscillator, it's in essence zero-point motion would correspond in essence to typically quantities that are in essence on the order of typical values between 10 to the 16, 10 to the minus 18 meters. So these are very, very in essence small displacements of these micromechanical oscillators. They're typically on a fraction of a proton diameter. So what it takes in essence to enter the quantum regime of mechanics would actually to develop tools with which you can in essence initialize mechanical oscillators in their ground state, and also develop kind of tools how to measure the mechanical motion. And these two challenges, in essence, have really fueled the field of cavity optomechanics over the last years, which is also, of course, what we hear more about in this session today. And let me mention, however, that optomechanics might be, in essence, a new development over the last years, but it suffices to say that there have been many proposals of how to control mechanical systems at the quantum level. And these go back to work, in essence, by Peter Zoller, for instance, or Atesh Moglu, and others that propose to couple mechanical oscillators to other quantum systems which can be well controlled. Okay, and what are these quantum systems? Well, for example, these could be trapped ions. They could be capacitively coupled, in essence, to mechanical oscillators, and you can use the ion, so to speak, to prepare the mechanical oscillator to cool it and to achieve, in essence, quantum control of a macroscopic degrees of freedom. There are other examples such as quantum dots embedded in nanomechanical beams, or SETs, so superconducting or single electron transistors coupled to nanomechanical oscillators. So these are all examples of proposals, some of them also experimentally implemented, of how to achieve, in essence, a control of the mechanical oscillator really at the quantum level. Now, kind of another route to achieve this control, and that's the route I will be presenting today, and that is also a session, is on coupling, in essence, the mechanical oscillator directly to the light field. Okay? And of course, we all know that lasers are extremely powerful devices when it comes to control of atomic motion. You can cool atoms of ground state, you can create optical lattices, you can look, in essence, at a variety of phenomena that all utilize, in essence, the optical field to both probe and prepare atomic states. And now the question comes, can you use these optical fields to also probe and prepare mechanical states of motion? Now, I would like to make a small historical remark. One of the first persons to really have thought about this kind of problem, however, slightly different context, was Vladimir Brzezinski. And Brzezinski proposed back in 1970 already that you can, in essence, consider the radiation pressure to be able to cool mechanical mirror motion. So what he considered here is the canonical optomechanical system, which we'll hear a lot about in this session, where you couple, in essence, a harmonically suspended end mirror to an optical field inside a cavity. And you can describe this by a very simple Hamiltonian. Okay? And this Hamiltonian couples A dagger A, the number of photons in the cavity, to X, the mechanical oscillator coordinate. And so what this interaction Hamiltonian allows you to do is, for instance, very sensitive displacement measurements. So if you were to displace the end mirror, okay, and you look at the reflected phase of the optical field, then actually the reflected phase contains information about the mirror position. And provided you have, for instance, a very high finesse optical cavity and a strong optomechanical coupling coefficient G, you can make very sensitive, in essence, precision measurements. Now, this is one proposal Brzezinski made, but he also made another proposal that's shown up here, or as early as 1970, which is quite interesting from a historical perspective, because he proposed already that you can use this optomechanical interaction to, in essence, laser cool mechanical motion. Yeah. And laser cooling for atoms was proposed about 5 years later, so it shows that these ideas have been around actually for quite some time. Now again, Brzezinski made these predictions all in the context of gravitational wave detection. He was interested in using interferometers, in fact interferometer pairs, to construct gravity wave interferometers. Okay, and gravity waves are tidal waves. So what they would do is they would, in essence, reduce the space or the length of one arm, increase the other, and differential length changes are extremely minute. So they're at a level of about 10 to minus 22 for typical astrophysical events people are thinking about. And that means you have to really worry about the influence of radiation pressure, okay, on these end mirrors, and in particular on the measurement process. Okay, and Brzezinski, for instance, was the first to point out, already in the 70s, that there is a standard quantum limit of how accurately you can monitor the motion of a mechanical mirror, which is subject to the quantum fluctuations of the laser field. Now again, this was a context for many decades, and again, all these optomechanical interactions and all this optomechanical physics was mostly, in essence, investigated in the context of these large macroscopic gravitational wave interferometers. And what has happened over the last, say, 6 years is that many of these ideas are now suddenly being rediscovered in a very different setting, and that's a setting of micro nanomechanical oscillators, because many of the ideas that were formulated for gravity wave detection also apply to small micromechanical oscillators coupled to optical laser fields. Now, just from a formal perspective, let me just note that this optomechanical interaction, in essence, allows you, in essence, for instance, to perform an operation which would be, in essence, equivalent to state swapping. So if you look, for instance, at, again, the Hamiltonian of the system, again, it's 8 o'clock in the morning, but let me make this comment. You can couple here, in essence, the optical laser field A dagger A, and this is written as a fluctuation terms here, to the mechanical oscillator, okay, coordinate. And the coupling strength between those two is given by the frequency pole parameter G, so that's actually how much the cavity frequency is shifted, okay, by elongating the mechanical oscillator. And it's actually now multiplied by the zero-point motion of the oscillator, so it's that small that the coupling constant can be quite large. But moreover, if you linearize the Hamiltonian, what you see here is there's a term A dagger, okay, or actually A bar. A bar is the root number of photons in the cavity. So that means actually that if you look at this interaction between optics and mechanics, it's actually enhanced by the mean field inside the cavity. And you can make that coupling coefficient larger by simply increasing the number of photons inside the cavity. Now, rewriting this a little differently, you see here that what you have is an Hamiltonian, which allows you, in essence, to swap, say, a photon into a phonon and vice versa. Okay, and the coherent coupling rate that describes this process is omega c, is now given by the so-called vacuum coupling rate, okay, G times x zero-point motion, times, in essence, the root number of photons in the cavity. And you can make that number, in principle, quite large, simply by providing a strong coherent drive field, which now couples the mechanical degree of freedom with the optical one. Now, if you look at, again, from a formal perspective, this optomechanical Hamiltonian accomplishes a rather interesting kind of interesting fact. It accomplishes to actually couple the mechanical oscillator, okay, to an optical laser field. And this coupling is parametric. I'd like to emphasize this because the mechanical oscillator here, in essence, has a frequency of typically a few tens of megahertz, okay, and the optical field, okay, lives at 190 terahertz. So you have here, in essence, a very wide disparity of frequencies, and you couple them, in essence, parametrically by this radiation pressure Hamiltonian. Now, what is interesting to also ask is what are the advantages of this coupling? And the advantages are the following. The mechanical oscillator, in essence, is a device, for instance, which lives, as I said, at low frequency. It can be made to interact with the environment. So it's actually uniquely suited to probe, for instance, phenomena whereas the optical field is very uniquely suited for detection. Okay, you have at room temperature almost zero thermal photons in the environment. There's quantum detection, and combining the both now allows you to address now, in essence, this question of readout of mechanical motion and also state preparation. Now, again, this is the interaction Hamiltonian written in a very idealist way, but you also have to ask yourself, okay, what are the other processes that could somehow destroy, in essence, the exchange, the coherent exchange of information or states between the mechanics and the optics? And the rate at which, in essence, the environment is destroying states, okay, is given by the decoherence rate. And if you look at the two environments now, these are quite different. Again, the optical field here lives at 190 terahertz, so there's almost zero photons in the environment. So it's a very cold photon bath, okay? Now, on the other hand, the mechanical oscillator sees an environment where kBt or h bar omega is very large, okay? So it has typically, at room temperature, maybe a few 100,000 of quanta that are in the environment that it can thermalize to. Now, this implies that if you ask now, what is the rate at which, say, for instance, a single phonon state actually would get destroyed, okay, in a mechanical oscillator, this is actually, in essence, described by the so-called thermal decoherence rate. And this thermal decoherence rate is simply the energy decay rate times the mean number of quanta in the environment. So this implies that even if you have a very, very high Q oscillator with maybe 1 hertz line width, if it resides at room temperature and is coupled to a high temperature bath, the rate at which quantum states get destroyed, in essence, becomes very fast, okay? And you can rewrite this expression also simply as kBt over h bar q. That's the relevant thermal decoherence rate. And this has to be contrasted with the rate at which optical information would get lost. So if you had, say, a single photon state in a cavity, okay, what would be the time it would take for the state to be dissipated? This thermal decoherence state, or decoherence time, will be given simply by the cavity decay rate kappa, okay, because there's, in essence, at room temperature, almost no photons, okay, in the environment, okay. Now, a very interesting regime now, and very interesting hierarchy of scales, is to achieve a coherent coupling rate, okay, omega c, which exceeds both, in essence, the rate at which, in essence, the optical photon field will get, in essence, or decays, decoheres, and also faster, and this is actually the difficult rate, than the mechanical decoherence rate, okay. Now, I'd like to explain to you now, in the remaining part of this talk, is an experiment where this hierarchy has been achieved. So where you can make the coherent coupling rate between light and mechanics, okay, where you can make that faster than both the optical decay, okay, the optical decoherence rate, but also the mechanical decoherence rate. And that's really, in essence, a regime where you can start about thinking of making quantum state manipulation, sending in a single photon, swapping this to the mechanics. Now, what is the system that we're using to probe these phenomena? The systems that we are using are, in essence, optomechanical resonators. And these are devices which couple an optical degree of freedom, in our case is a whispering gallery mode inside a microtoroid, okay, to a mechanical degree of freedom. Okay? The mechanical degree of freedom here, in this case, is a radial dilatation mode, so a periodic elongation, in essence, of the cavity radius. And inside these toroidal resonators, the frequencies of this mode are typically about 70 to 90 megahertz. So these are, high frequency radial dilatation modes. And these are coupled now to whispering gallery modes. And these optical whispering gallery modes have very high Q. Their line width is typically a couple of megahertz, corresponding to quality factors that are typically around 100 million. Now the coupling, okay, in these structures can be very large, simply because you have here a co-localization of the optical mode and the mechanical mode, and the masses of these structures, compared to, say, these early work on this gravity wave detection, these are very small. Now, how can you probe this optomechanical interaction? Well, first of all, as I mentioned, the radial breathing mode is coupled to the optical field. So what happens is that if you couple light, in this case we couple via tapered optical fiber into the cavity, then in essence the Brownian motion will imprint phase fluctuations on the light. Okay? And you can measure these phase fluctuations with a Hamiltonian detection scheme. And if you do so, you can retrieve, in essence, a photocurrent that's proportional to, in essence, the phase excursion, okay, caused by the mechanical motion. And if you Fourier transform this, you get what we call a typical noise spectral, or in essence, a noise spectral density. And this tells you, for instance, here that you have a mechanical oscillator at 60 megahertz. From the line width here, you can tell the optical Q, or mechanical Q. And what's kind of important for the context of this talk is that the area underneath these graphs here, this area is proportional to temperature. Okay, so by virtue of the fluctuation dissipation theorem, the variance in essence of the or the area of the Brownian motion here gives you in essence a quantity that's proportional to temperature. So if you were to cool the mechanical oscillator cryogenically, for instance, you would see that this area reduces. Now, how can you reach this kind of coherent coupling regime, and what makes it really difficult? Well, as I mentioned, the first challenge is to make this coherent coupling rate very large. And the way you can do this is simply by, first of all, increasing the number of root number of photons in the cavity and making the vacuum coupling rate of the light mechanics very large. And here, in essence, you have all the, in essence, tools of microfabrication at your disposition. You can, for instance, make this vacuum coupling rate large by simply shrinking, in essence, the cavity radius, because this factor scales as omega over r, and making the zero-point motion of the oscillator large. So here, in essence, just engineering of the structure can give you, in essence, a large value of G naught. Now, the second aspect is, even if you have a large coherent coupling rate, you still like the mechanics in the light field to interact faster than a thermal decoherence rate. And this thermal decoherence rate is proportional, in essence, to the inverse Q of the mechanical oscillator and directly proportional to temperature. So it's clear that if the mechanical oscillator is in a very low temperature environment, you can make the thermal decoherence rate very, in essence, very low. And so what we have taken, or the route we have taken in our experiments, is kind of twofold. First of all, we've engineered this G naught, and so we have made toroidal resonators with spokes. And in these structures, you can really augment the vacuum coupling rate to quite appreciable levels of about, in essence, 1% of the cavity line width. So typically about 3.5 kilohertz. And the spokes here really have, in essence, a dual role. On the one hand, these spokes actually, what their serve is, they serve to reduce clamping losses, okay, via the pillar of this on which the structure is residing. But at the same time, what they also do is they make the structure more compliant. Okay, so the structure is spring constant, but the insertion of the spokes also reduces. And that's useful because actually that actually increases the zero-point motion and thereby also increases the G naught, the vacuum coupling rate. So this is in essence how we engineer, using finite element simulation, the mechanical losses and also the vacuum coupling rate. Now, these are some fabricated structures we made at EPFL. So you see here the diameter of these bridges here is about 500 nanometers. I'd like to mention that also the typical design parameters which we need for these structures, they're not completely trivial. So typically in MEMS, one typically uses as a length a quarter wavelength for the phonon. In these structures, that's not completely the case. So you really have to simulate the entire structure to take into account all the flexural modes and all the hybridization to achieve a structure that has low mechanical losses. Now, this structure now we can couple. We can couple this in a very low thermal environment. And the way we proceed in our experiments is we have an optical fiber, a tapered optical fiber, that we use to near field, in essence, excite the Whisper gallery modes of this toroidal resonator with spokes. And this whole structure is embedded in a helium-3 buffer gas cryostat. So this is a cryostat which prepares via helium-4 a cold helium-3 buffer gas at a temperature of typically 600 millikelvin. And despite being a very low temperature, you still have at these temperatures about 180 to maybe 250 quanta. Okay. What's very kind of advantageous about a buffer gas is you can achieve a very good thermalization. So if you look at the temperature of the cryostat, okay, and you look at the temperature of the mechanical mode inferred by this area theorem I mentioned earlier, then in fact you see a completely linear relationship, okay, up to the lowest temperatures. And that's kind of expected because the buffer gas, in essence, surrounds the entire sample, the fiber, so you get a very, very good thermal anchoring. And I should mention this is not completely a priori trivial because you get this very, very small pillar here. So if you were to anchor the device, say, on a normal flow cryostat, you would not be able to achieve the same, in essence, performance of thermalization. Now, what we can also look at now is the mechanical quality factors. And there's some very interesting physics, actually, that relates to the mechanical damping at low temperatures that I won't have much time actually to go into. But I'd like to mention that all the losses we're seeing, they don't come from the clamping losses, so from the anchor point, but they are uniquely related, actually, to the structure of glass itself. And these are called defect states, and they're been known, in essence, since the 70s to play a role in the thermal properties of amorphous solids. And at the lowest temperatures of about half a Kelvin, the highest quality factors we achieve are more than 20,000. And so these are very decent values. These are QF values of greater than 10 to the 13. And they allow us to do the type of experiments that I'd like to present in the next slides. Now, just a quick outline of the experiment. So we see here the optical cryostat. And in essence, at the very, very bottom, there's this tiny toroidal resonator coupled to the optical fiber. And in essence, to laser cool the devices, what we do is we use a titanium sapphire laser. And this adds quite a bit of complexity to the experiment. But there's a good reason to do so because, in general, we need a very cold photon bath. Okay. And for this, it's not just sufficient to be at high frequency, but we also really need to avoid any excess phase noise. And it's quite well known that, for instance, diode lasers have phase noise, relaxation oscillations, which can have very high frequencies. They can have peaks between 3 and 4 gigahertz typically. If we take a Thai sapphire laser, okay, due to the very large cavity length and also the fact that the relaxation of the transition is lower, we can move that relaxation oscillation frequency down to typically values that are much lower than our 70 megahertz of the mechanical oscillator. So in this way, in essence, we achieve a level of phase noise which is actually sufficient for experiments that can prepare mechanical oscillators in that quantum ground state. Now, it turns out these experiments also, phase noise in the laser is one source of phase noise, but there's another interesting source I'd like to briefly just mention. Even if you have a laser that is quantum limited in phase and amplitude, it turns out one has to really worry about the optical fibers. Okay, and in fact, if you do a Hamiltonian measurement, okay, at low temperatures, what you see here is that the shot noise background is not flat. Okay, and that tells you that there's really an excess noise contribution coming from the experiment. And this excess noise contribution comes from the fact that an optical fiber also has mechanical modes. Okay, so the radial dilatation mode of the fiber itself, okay, which breathe at room temperature. So if you send an optical laser through a fiber, it also picks up a phase modulation. And this has been studied in the context of squeezing in the 80s, and we can also see them in our experiments. So if you look at our Hamiltonian detection signal, what we see is several bumps here on top of our background. So clearly we're not shot noise limited here. If you now actually remove the buffer, so the acrylic of the optical fiber, these peaks become very sharp, okay, exactly as we'd expect, in essence, for an undamped guided acoustic wave mode. And what we can do now is we can simply etch the fiber and actually move the frequency of this mode away and create a region actually where we can really substantially reduce this excess phase noise. And that's extremely critical for all these experiments because the phase noise in the laser is imprinted on the mechanical oscillator. So to be able to access the quantum regime, we need to ensure that this phase noise is at a sufficiently low level. Now, what we can do next is probe, in essence, our mechanical oscillator in his low temperature environment. And the way we do this is we send in our titanium sapphire laser, and in the first measurement, what we do is instead of actually sending in just a single laser beam into the resonator, we send in actually several laser beams created by a phase modulator, and we record what we call, in essence, the coherent response measurement. And what this implies is the following, that you have a laser sitting, for instance, here, away from the cavity. If we scan now a weak sideband over the cavity, we can see the cavity dimension, so that gives us the width here. We also see a small oscillatory feature, which comes from the optomechanical interaction. And that's the feature, in essence, that is quite similar to a feature that is known in atomic physics. That's called, in essence, EIT. This is an EIT feature which comes from the optomechanical interaction, which, in essence, dresses the optical resonance and gives a width or a transparency window whose width is scaling with the coherent coupling rate, omega c. Okay, so from these measurements, we can actually deduce uniquely, actually, how strong this coupling of the optical field to the mechanical oscillator is via this phenomenon of what we call optomechanically induced transparency. And this phenomenon, by the way, is quite interesting also to actually slow down optical pulses via this very narrow interference feature. Now, this is what we call the coherent response, and again, it uses here not just the strong coupling laser, but also a weak sideband. We can also now turn these sidebands off and look at the so-called incoherent response. Okay, so here we just propagate our cooling laser, in essence, into the mechanical oscillator and use Hamiltonian detection to retrieve, in essence, the Brownian or the fluctuation spectrum. And if we do this, in essence, then you can record a Brownian noise spectrum for each of these laser detunings I mentioned before. Okay. Now, what we see, for instance, if the laser is very far away from the lower sideband, we expect that there's a very weak coupling between the optics and the mechanics. And this is also the case. So we see a Brownian spectrum which corresponds to about 200 quanta. And that's actually exactly the number of quanta we expect for our buffer gas pre-cooling to 600 millikelvin. Now, if we increase, in essence, now the laser detuning close to the lower sideband, and what we can see is that we start to cool the mechanical oscillator. So we see here that now we are reducing the occupants to about 11 as we approach the lower sideband of the mechanical oscillator. Now, precisely on the lower sideband, and this coincides with the region where we have this very narrow transparency feature, the lowest occupants which we can achieve is about 1.7 quanta. Okay? So it means that the oscillator here now spends away about 37% of the time in its quantum ground state. Now, I'd like to mention that acquiring these spectra is extremely fast, so we take about 30 seconds of averaging. And the reason is because we have this optical fiber, and all the information about the mechanical motion is immediately transferred back into this fiber and can be used for, in essence, Hamiltonian detection. Now, what is this cooling rate limited by? In this case, the cooling rate is limited by the fact that we have a cooling rate here that is almost as wide as the cavity decay rate. So we are reaching a regime where, in essence, the coherent coupling rate between light and mechanics is both faster than thermal decoherence, but also starts to be comparable actually to the cavity decay rate. Okay, so this implies that the thermal state of the mechanics is swapped in essence to the optics, and then swapped in here into the very cold bath. But in fact, we start to be limited here by the cavity decay rate into the environment. And this is in essence the onset of the so-called strong coupling regime. Okay. Now, we can also look in essence at these data slightly differently. We can plot, for instance, the occupancy as a function of laser detuning. And what you expect here is that exactly on the lower sideband, the occupancy in essence is most strongly reduced to about 1.7 quanta. Now, what you can do next is also you can increase the laser power. And the way you can do this is, what it entails now is that the coupling rate will get even stronger. So it will now start to exceed, in essence, the cavity decay rate. Okay. Now, this can be seen in this data here. So here again, there's the optical spectrum. So there's optical probing of the transmission spectrum. And then there's also, again, this incoherent probing of the mechanical displacement spectrum. And what's shown here, in essence, is two detunings. Okay. The lower detuning here, in essence, is the offset from the laser frequency. The detuning here is, in essence, just the Brownian fluctuation spectrum. And on the vertical axis, there's a laser detuning. Okay. So if you look at the laser detuning, which corresponds to the mechanical oscillator frequency at about minus 80 megahertz, what you can see is that the optical spectrum splits into two branches. Okay. So what happens here is you have a hybridization of the optical mode with the mechanical mode, and it gives rise, in essence, to polariton. Okay. So it's a very similar physics that you have in strong coupling, both in semiconductors to optical cavities or in cavity QED. So there's just a polariton splitting of the optical branch. And what you can also look at is the mechanical displacement spectrum, and you also find the same. You also find that the mechanical spectrum now consists of two peaks, okay? And these peaks have a width, in essence, that's given just by kappa plus gamma over 2, so just by the weight of the optical decay and the mechanical decay. Now, clearly, the coupling rate between optics and mechanics exceeds now the decay rate of the optical field. And what you can also ask the question now: does the coupling rate also exceed, in essence, the thermal decoherence rate? Now, you cannot tell from this picture, okay, if the coupling rate also exceeds the thermal decoherence rate. These are all classical signatures. So what you have to do is you have to, again, look into the mechanical domain and ask what is the relevant thermal decoherence rate. And you can measure this by, again, using an integrated, in essence, noise spectrum analysis. And for the measurements that we perform on the lower sideband, we can actually achieve a regime where, in essence, the coherent coupling rate is equal to the mechanical optical decay rate, but also equal to the thermal decoherence rate. In fact, in our measurements, we see that the thermal decoherence rate is not constant over laser detuning range here, but also increases. And that's expected because as the laser moves closer to the cavity, we start to put more photons in the cavity, and we have residual heating. Okay, so this is just, in essence, the Lorentzian absorption profile of the cavity that gives us actually a slightly higher temperature of the mechanical oscillator, deteriorating our thermal decoherence. Now, precisely at this point here, we, in essence, reach a regime where omega c is comparable to kappa and gamma, and that's really, in essence, what provides now the opportunity to venture into experiments that utilize, in essence, a mechanical oscillator really as an element to store, for instance, quantum information. Now, we are not the first to achieve this regime. This regime has been achieved in 2 experiments before, by the group of O'Connell, Santa Barbara, and also by Conrad Lehnart's group. But these two were experiments where this hierarchy was, in essence, satisfied using microwave fields. And we can do this now also in the optical domain. And again, the optical domain has the big advantage of, for instance, having an availability, for instance, of single photon sources that one could use for such experiments. And just one example of how in the future one could proceed, if in addition to the strong coherent drive field, you injected, for instance, a single photon source. In our case, we did a classical experiment by replacing a single photon source with just a very weak coherent drive. If you inject this very coherent drive into the cavity, what we see is that the mechanical displacement and the optical displacement spectra, they in fact show these oscillatory features where you can see the strong coupling here in the optical temporal domain. And if you look, in essence, at the decay rate of the optical field, okay, in the presence of this strong coupling, what you can see is that the optical field now does not decay with kappa, but with kappa over 2. So there's a slightly longer decay time, and that's expected because half of the time the optical energy resides in the mechanical oscillator. So this is a signature here of, again, this strong coupling regime. Now, if you were to do this experiment instead of with very weak coherent states, rather with single photon sources, this could provide a very interesting outlook for the future, because this could allow you now to, for instance, swap a single photon into a phonon and thereby create, for instance, non-classical states of mechanical motion and really use the quantum properties of the mechanical oscillator. So with this, I'd like to thank you for your attention, and I'd like to summarize. I've described to you, in essence, toroidal optomechanical systems we have been studying. We've been pre-cooling them to temperatures about 600 millikelvin to achieve this desired hierarchy of coherent coupling. And in the future, we'd like to really probe, in essence, the quantum properties of this system in conjunction with single photons. Thank you so much.